and practically, both for conceptual purposes and practical purposes, which I'll review and explain further along in my talk. Also, I should point out a major advantage that we have in the modern in modern developments, which the old S-matrix theory paradigm people didn't have, is that we actually know the answer. You know, in cases where we ever get stuck, we can go look up the QCD Lagrangian. So you know that it's often much easier to make progress on a problem where, you know, it's like you're given a homework exercise. It's much easier to do a homework exercise that says, prove that, and then the answer is given. That's much easier than trying to solve a homework problem where you're not given the answer. So first of all, let me convince you that we actually have a problem, namely that there is actually something interesting going on in the scattering amplitudes of massless vector particles. So let's consider one of the simplest things you could possibly imagine. Suppose you took it upon yourself to calculate a tree-level scattering amplitude of 5 gluons. Okay, something you might think, well, this is a complete triviality. Well, if you sit down and start thinking about it, you'll realize that there are 25 different Feynman diagrams you can draw. Okay, that's not so bad. But then you look up in the appendix of your favorite quantum field theory book, you look up the Feynman rules for gluons, and they're rather messy. Each cubic or quartic vertex involves some long expression, which, depending on how you count, has of order 3 or 6 terms, something of that order. So a typical Feynman diagram here requires you to multiply two vertex factors, or sometimes in some diagrams 3 vertex factors with each other. So pretty soon you can see that if you were to write this all out, you would get quite a bit of mess. It would span many, many pages. Magically, however, people have known for several decades that regardless of the complexity of intermediate steps in this calculation, the final result turns out to be incredibly simple. And so here I'm going to denote, the left-hand side denotes a tree-level scattering amplitude of 5 gluons. The plus and minus denote the helicity of the particles. Of course, massless vector particles carry 2 polarization states, just like you're familiar with the photon. So suppose we're interested in a scattering amplitude where 3 of the particles have positive helicity and 2 of them have negative helicity. And suppose the 2 particles are with negative helicity are I and J. Then I will quote without proof for you that the result for that scattering amplitude, after you sum all the 25 Feynman diagrams, and if you're lucky enough to see all the right cancellations to do, the answer boils down to just that single term in a notation which, if you're not yet familiar with, I will introduce in a couple of slides. But the upshot from an exercise like this, you know, even if you don't particularly care about the value of this 5 gluon amplitude, you ought to find something rather striking, which is that simplifications like this don't happen in physics by accident. If you have a situation where you're doing a calculation and intermediate steps take of order 20 pages, and the final result simplifies down to a single expression like that, then that should signal 2 things to you. First of all, that you're thinking about the problem the wrong way. And second of all, that for whatever calculation you are interested in, say you're interested in some other scattering amplitude, it behooves you to understand that deeper structure so as to make further calculations more efficient. Let me give you an example of that. Suppose you were to calculate a 1-loop 6 gluon scattering amplitude. Here I've taken from a nice talk by Carola Berger a picture showing you some of the representative Feynman diagrams, which for this process would fill approximately 30,000 pages just to list the Feynman diagrams. You know, not even to write them all out in terms of the horrible Feynman rules which I wrote for you a few slides ago. Nevertheless, this particular result for this calculation is, quote, trivial with modern methods. So this is obviously should be a signal to you that there's some better way of organizing these kinds of calculations. Now again, I feel given my disparaging comments earlier about the fact that our universe has no massless vector particles, I want to come back to the question of who cares and emphasize the importance of these developments. And I can do that by saying that I may not know much about what the LHC might perhaps see. We're all hoping that the LHC will discover the Beck particle. Perhaps the LHC will discover supersymmetry, strings, or something more exciting like Earth-devouring black holes. But there's one thing I know for sure. I know for sure that the LHC will see lots and lots of QCD background, right? So in order to miss any minute signs of new physics that might be hiding amongst the monstrous haystacks of data that will be coming out of the LHC, it really is incumbent upon us to understand in as great detail as we can and in as much precision as we possibly can the precise values for expected QCD backgrounds for, well, hopefully all relevant processes. That's too much to hope for, but as much as possible we should understand. And this has led to a series of challenges which the experimental community has posed to the theoretical community over the years, usually called experimentalists' wish lists. So here's one that was formulated in Les Ouches 2005, and again I've adapted this from a talk by Carla Berger, who nicely looked this all up and summarized this. So these are just examples of so this is these are QCD backgrounds relevant for LHC physics, which experimentalists would like to know precise next deleting order, that is one loop, usually one loop, corrections to. Here's an updated list from 2007 in which a few of the items had been completed or had partial results. And of course, they also added several new things to the list. Can't resist making our lives harder. And here's an updated list from 2010. So after the new methods and ideas that I will be talking very briefly about have had time to germinate and really make their mark upon the community. Okay, so I hope I've convinced you not only that there is